어떤 명제가 너무 커서 한 번에 증명하기 어려울 때가 있습니다. 그럴 때 가능한 경우를 빠짐없이 몇 갈래로 나누고 각 경우에서 따로 증명하면 어떨까요? 이게 바로 오늘 우리가 함께 볼 경우 나누기의 핵심입니다. 그 전에 이미 우리 손에 있는 증명 도구들을 먼저 같이 떠올려 봅시다. 증명 방법은 외우는 게 아니라 명제의 첫 모양에서 나오는 첫 수거든요.
Just a recap of where we were last time. As we've seen, we're growing our catalog of different proof techniques of how to prove different types of theorems, almost by like a cookbook. If you want to cook this, here's how you get started. And so here's a brief summary of this. If the theorem you want to prove starts with there exists something, then a natural way to prove that is by example or by construction. You construct a particular x star and prove that p of x star is true. And if you can do that, then you've proved that there exists an x where p of x is true. It's kind of straightforward, but it lets you unwrap. If I give you an expression that starts with exists, then you know your first step is try to figure out an x where this is true. And of course, to prove p of x star, you probably recursively use this cookbook. If you want to prove a universal, one common way, if you want to prove for all x, p of x is true, typically your first line is take an arbitrary x, just give it a name x, and then prove that p of x is true no matter what x you started with, therefore it's true for all of them. Come back to induction in a second. If the main thing you want to prove is an implication, p implies q, this is if p, then q. And I want to remind you that p implies q is the same thing as not p or q. We'll use this a bunch today. Then the direct way to prove this, what we call a direct argument, is assume p is true and then prove q is true. Because this implication, we only need to prove that q is true when p is true. If p, then q. Or another way to prove that same statement, p implies q, is what's called the contrapositive. It turns out p implies q is the same statement. It's equivalent to not q implies not p. Remember, this symbol is a negation. Flip true and false. So to do that with a direct argument, we would prove that if not q is true, then not p is true. In other words, assume not q and then prove not p. This may seem kind of magical. Why is p implies q the same as not q implies not p? But it actually follows directly from this equivalence. If you look at not q implies not p, this is the same thing as, let me go over here, not q or not p. Right? Because it implies it's the same thing as taking an or if you negate the part on the left. And not q is the same as q. Okay, so this was not q implies not p. It's the same thing as this, is the same thing as this, and that is exactly this, just by switching the order of the ors. And so p implies q is the same thing as not q implies not p. More.
방금 함께 짚은 게 바로 증명의 기본 요리책이죠. 여기서 핵심은 정리의 첫 기호를 보면 어떻게 시작할지 알 수 있다는 겁니다. 예를 들어 어떤 x에 대해 px라면 맞는 예를 딱 하나만 만들면 됩니다. 반대로 모든 x에 대해 px는 특별할 것 없는 임의의 x를 잡아 증명합니다. p이면 q는 두 가지 방법으로 증명할 수 있습니다. p를 가정해 q를 보이거나 대우인 not q이면 not p를 보입니다. 이 셋은 외울 사실이 아니라 명제의 문법에서 나오는 첫 수입니다. 이어서 좀 더 거꾸로 가는 수를 봅시다. p가 아니라고 가정해서 증명하는 방법이죠.
So that was contrapositive. There's a related notion of contradiction, where if you want to prove any statement p, you assume that not p is true, and then find a contradiction. Prove that, in fact, false is true, or something is both true and false. All these things are very, very bad, because we assume that our axioms are consistent. And so if you can prove false, that means that what you assumed must also be false. And if not p is false, that's the same thing as saying p is true. Feels very backwards, lots of double negatives in there, but that's the nature of contradiction. We try to avoid them when we can, but sometimes it's really the right way to prove something. And the last technique we saw was induction, where if we have a universal quantifier over the natural numbers, we want to prove p of n is true for all natural numbers, 0, 1, 2, 3, and so on, then we only need to prove it for some base case, p of 0, and then we need to prove that p of n implies p of n plus 1 for all n. So we'll talk more about induction in a little bit. Today, we're going to add to this list 2 more proof techniques. One is proof by cases, and the other is strong induction. So proof by cases is just a nice general technique to be aware of. It can be very powerful. Strong induction is going to be an even cooler form of induction. All right, but we'll start today with proof by cases. And we'll start with proof by 2 cases.
방금 본 두 도구, 모순과 귀납은 둘 다 거꾸로 접근한다는 공통점이 있습니다. 모순은 참인 걸 보이려고 일부러 그게 거짓이라고 가정합니다. not P, P가 아니라고 했을 때 거짓이 따라 나오면 그 가정은 버틸 수 없습니다. 그래서 P가 참이 되는 거죠. 다만 이건 우리 공리계에 모순이 없다는 전제 위에서만 성립합니다. 귀납은 자연수에 대한 명제를 다루는 또 다른 방법입니다. 기초 단계를 보이고 Pn이면 Pn 플러스 1을 보이면 모든 경우가 차례로 참이 됩니다. 이제 방향을 바꿔봅시다. 어떤 명제시든 참이거나 거짓이라는 사실로 증명을 둘로 나누어 보는 겁니다.
So, the idea is take any proposition C and observe that C or not C is a tautology, meaning always true. Okay, if C is true, then this whole thing is true because C is true. If C is false, then not C is true, and so this whole thing is true. I'm going to remind you this so V symbol is an or, whereas the opposite symbol is an and. I think the mnemonic here is this looks like a letter A. This looks like a letter O. I've heard some people say this looks like a lowercase r for or. Anyway, you just remember these things. This is or, this is and. So C or not C is the question. No, is always true. So we call it a tautology, fancy word for being always true. And so what this tells us is that our proposition P, let's say we want to prove P, is equivalent to C or not C implies P. So this is saying if C or not C, then P is true. C or not C is just always true. So this is saying if true, in other words, always, P better be true. So P and this implication are equivalent. Another way to see that is to rewrite this implication as a negation, I guess. So this is like saying not true or P. And so that's just the same thing as P, because this is true. Okay, cool. So I want to rewrite this a little bit and say this thing is equivalent to C implies P and not C implies P. Why is this true? It's like a distributive law. This is saying I want to prove that C implies P, and I want to prove that not C implies P. That's what I wrote over there. That implies that the combination of C and not C implies P. Okay, so I claim these are equivalent. One way to verify it is with the truth table, or you can do it with some manipulation. All right, so we have
경우 나누기가 왜 정당한지 그 바탕에는 단순한 사실이 하나 있습니다. 어떤 명제 C를 가져와도 C 또는 not C는 항상 참입니다. 이렇게 항상 참인 명제를 항진 명제라고 부릅니다. 이 사실 덕분에 P 하나를 증명하는 큰 문제를 두 개의 작은 조건부 증명으로 바꿀 수 있습니다. 정확히 말하면 P 증명은 C이면 P와 not C이면 P를 둘 다 증명하는 것과 같습니다. 예를 들어 정수 n에 대한 주장이라면 C를 n은 짝수다로 잡아봅시다. 그러면 모든 정수가 짝수 n과 홀수 n으로 갈리고 세 번째 경우는 없습니다. 여기서 조심할 점은 경우 나누기가 그냥 서술 방식이 아니라는 겁니다. 경우들이 빠짐없이 전체를 다룰 때에만 유효합니다. 그래서 다음에는 이 경우들을 어떻게 하나의 틀로 정리하는지 같이 봅시다.
What this is saying is, in order to prove P, we need to prove that P is true assuming C, and prove that P is true assuming not C. And these are the two cases. In a proof by cases, let me write out a little template for you. Let's suppose the theorem we want to prove is P. Theorem means something that's true and that we're about to prove. And so we'd usually say proof by cases on the truth value of C. So this is for any statement C. Proposition is what the word I was looking for. Any proposition C, it's either true or false. And so we're going to do proof by cases on the truth value of C. Case 1 is that C is true. And case 2 is that C is false. And so what do we do in each case? Well, in the case that C is true, this means that we get to assume that C is true. And then use that to prove that P is true. And so the missing step in this proof outline or this template is we need to say P is true because some reasons, which we need to fill in. And similarly, in the C is false case, we need to prove P is true for some reasons. Okay, so we need twice as many reasons, but the idea is that maybe assuming C is true makes it easier to prove P is true. Maybe also assuming C is false makes it easier to prove that P is true. So in these boxes, here we get to use C, and in here we get to use not C. And often this makes proofs easier, but the challenging part is to pick the correct C. What's the right choice of C for this to be true? And maybe one more line I want to add to this template, which is pretty obvious in this setting, but gets much less obvious when you think about more than two cases. So a final step in this proof would be to say C is either true or false, because all propositions are either true or false. And so the cases are exhaustive. So this is also called a proof by exhaustion, not because we're really tired, maybe we are also, but the idea is we want to exhaust all possible cases, and if we prove that we captured every possible situation and all of them P is true, then we're done. Okay, so that's what we'd like to do. I'm going to give you two examples. First one is very simple. The second one is more interesting.
이 틀은 두 가지 일을 동시에 합니다. 글을 정리해주고 동시에 논리가 새지 않게 지켜줍니다. 경우 하나에서는 C를 가정하고 P를 증명합니다. 다른 경우에서는 not C를 가정하고 다시 P를 증명합니다. C 또는 not C가 모든 가능성을 빠짐없이 다루니 P는 조건 없이 성립하게 됩니다. 각 경우에서 두는 가정은 반칙이 아닙니다. C가 늘 참이라거나 늘 거짓이라고 우기는 게 아니라 어느 경우든 P가 성립한다고 말하는 겁니다. 구체적인 예로 n제곱이 n과 같은 짝호를 가진다는 걸 봅시다. n이 짝수면 n제곱도 짝수, n이 홀수면 n제곱도 홀수입니다. 짝수와 홀수, 이 둘로 모든 정수를 빠짐없이 다루죠. 약한 경우 나누기는 보통 경계가 흐립니다. n이 작을 때와 클 때처럼 기준 없이 나누거나 중간 경우를 빠뜨리는 식이죠. 이 틀을 가지고 이번엔 순수한 논리 명제 하나에 적용해 봅시다.
So the claim is, this is a general fact, that A implies B or B implies C is a tautology. So this means it's always true. Again, so you can rewrite this as for all A, B, and C, which are either true or false, we have that A implies B, or B implies C is true. Okay, fun facts. Let's prove it. And the proof technique we're going to use by two cases, namely on B. B is either true or false. We could try to do a case analysis in terms of A or in terms of C. Turns out B is sort of the right answer here. It will lead to the fewest cases. We'll only need two. Intuitively, because B is in both of these expressions. So it seems good to split on B because it will impact this one and this one. Okay, so case one is that B is true. Okay. If B is true, I claim that A implies B is true, which is this first half. Why? In other words, I claim that A implies true is a tautology. I think an easy way to see this is to rewrite this implication as not the left-hand side or the right-hand side. Right? Not A or true. Well, that's just true. True or anything is true. Okay, so in particular over here, not A or B is true because we just assumed that B is true. Okay, so this tells us that A implies B or anything, in particular B or C, is also true. Okay, so kind of trivial, right? If you assume B is true, then of course this is true, and so of course the whole thing is true. So easy when you have the correct case. Let's think about the other case. It's not enough to just have one half of the cases. We also need to think about when B is false. When B is false, I claim that the other term is true. I claim that B implies C is true. This is maybe a little less intuitive. This is saying that false implies C is a tautology. Like for any C, false implies it. This should eventually become intuitive for you when you get used to implies and if-then. This is saying if false, which means never, I need C to be true. But if this condition is never true, then I don't care about the right-hand side. If pigs fly, then I don't know, apples are orange or something. That's a true statement because it will never be the case that pigs fly, or at least in the present time. So another way to see that is to think about, again, not B or C. B is false, so not B is true. And so, of course, true or C is also true. Okay, and so that tells us that anything or B implies C is also true. So in other words, this statement, which maybe I'll call P, I'll say in either case, P is true. And so I write my little end of proof symbol. This is QED from last time. This means that I have demonstrated the theorem.
이제 경우 나누기가 그냥 쪼개기만 하는 게 아니라 어디서 쪼갤지를 잘 고르는 일이라는 걸 이번 예제로 같이 봅시다. 정리는 이렇습니다. A이면 B 또는 B이면 C는 항상 참이다. A, B, 그리고 C의 참거짓이 무엇이든 상관없이 말이죠. 여기서 나눌 기준으로 B를 고르는 게 자연스럽습니다. B가 양쪽에 다 들어있기 때문이죠. B가 참이면 A이면 B가 저절로 참이 됩니다. B가 거짓이면 이번엔 B이면 C가 저절로 참이 되죠. 이게 되는 건 X이면 Y가 not X 또는 Y와 같기 때문입니다. 그래서 무엇이든 참을 함의하면 참이고 거짓은 무엇이든 함의해도 참입니다. 전제가 거짓이면 함의가 무의미하다고 오해하기 쉽습니다. 하지만 고전 논리에서는 전제가 참인데 결론이 거짓인 판례가 없으니 그 함의는 참입니다. 이제 같은 방법을 좀 더 그림에 가까운 문제에 써봅시다. 6사람이 있고 모든 짝은 친구거나 낯선 사이 둘 중 하나입니다.
Cool. So in one case, this part was trivial. In the other case, this part was trivial because it's an or we're happy in either case, and we've done our first proof by cases. Pretty straightforward. Let's do a more surprising result using proof by cases called mutual friends and strangers. This is actually a famous mathematical problem. We're going to solve today a particular case of it, which is, suppose you have 6 people, and every 2 of them are either friends or not. And this is an exclusive OR, so I'm going to write XOR. You're allowed to be friends or not friends, not both and not neither. And in the not friends case, I'm also going to call them strangers. So this is like extreme friendship. Either you declare yourself as friends or as knowing each other, or you don't know each other. In that case, you're strangers. You're just never both, and it's always one or the other. Okay, so you can think of this as I can draw a little picture of their 6 people represented by circles. You can put smiley faces in them if you want. And maybe I connect them via a white line if they are friends, and a dotted line if they're strangers. So and every 2 of them have one of these 2 pictures. Probably missing some here. Okay, that's them all. Then I claim no matter what the situation is, which ones are friends, which ones are strangers, there's always either 3 mutual friends or 3 mutual strangers. Okay, in this example, hopefully I drew enough. Yeah. These 3 people are mutual strangers. They're connected by a triangle of dashed lines. Okay? If I drew some other pattern, like if they were all solid lines, then I might get the other situation, at least 3 mutual friends. But it turns out if you have 6 people, there are always at least 3 mutual friends or 3 mutual strangers. Let's prove this by cases.
이 친구와 낯선 사람 문제는 경우 나누기를 그래프 문제로 바꿔줍니다. 사람 한 명을 점 하나로 두고 2 사람 사이는 정확히 한 종류의 관계로 있습니다. 친구면 실선, 낯선 사이면 점선입니다. 여기서 베타적 논리합, 즉 XOR가 중요합니다. 2 사람은 친구거나 낯선 사이지 둘 다이거나 둘 다 아닐 수는 없습니다. 목표는 운 좋게 삼각형 하나를 그려서 찾는 게 아닙니다. 6사람의 어떤 관계 그림에서도 서로 모두 친구인 3명이나 서로 모두 낯선 3명이 반드시 있다라는 걸 증명하는 겁니다. 서로 친구인 3명이란 그 셋 사이 세 관계가 모두 친구 변이라는 뜻입니다. 서로 낯선 3명이란 그 세 관계가 모두 낯선 변이라는 뜻이고요. 바로 여기서 경우 나누기가 큰 힘을 발휘합니다. 모든 관계망을 하나씩 확인하는 대신 한 사람을 고릅니다. 그 사람에게서 나가는 5개의 관계를 세고 거기서 쓸모있는 경우 나누기를 끌어내는 거죠. 오늘의 핵심 모델은 단순합니다. 증명 방법은 목표의 논리적 모양을 보고 고른다는 겁니다. 존재, 임의, 함의, 모순, 귀납, 그리고 오늘의 경우 나누기까지 저마다 다른 첫 수를 줍니다. 경우 나누기가 통하는 이유는 2가지입니다. 첫째, 경우들이 모든 가능성을 빠짐없이 다룹니다. 둘째, 각 경우 안에서는 증명이 한결 쉬워집니다. 이 방법은 6사람 문제에서 특히 잘 통합니다. 엉켜 보이던 6사람의 관계망이 의외로 빈틈없는 구조로 정리되는 걸 다음 시간에 같이 보겠습니다. 6명만 모이면 그 안에는 서로 다 아는 3사람이거나 서로 전혀 모르는 3사람이 반드시 있습니다. 우연이 아니라 반드시 그렇다고 증명할 수 있는 사실이죠. 증명에 들어가기 전에 바탕에 깔린 전제 2가지를 먼저 짚고 갈게요. 첫째, 두 사람은 친구거나 낯선 사이, 둘 중 정확히 하나입니다. 그래프로 보면 실선 아니면 점선이죠. 둘째, 경우로 나누는 건 찍는 게 아닙니다. 예, 아니오로 답이 갈리는 기준을 골라 문제를 더 단순한 형태로 바꾸는 거예요. 그래서 오늘의 핵심 질문은 이겁니다. 아무나 한 사람 P가 어떻게 혼자서 친구 삼각형이나 낯선 삼각형을 강제할 만큼의 정보를 이미 품고 있을까요?
Whenever we apply proof by cases, we need to come up with some proposition C that's either true or false. Well, for proof by two cases, which this will be. And it's a little work in this case to do it. It turns out a useful first step is to pick any person P. So just take the first person or the seventh or the fifth person out of six. Doesn't matter which one, but label it P. So now we have a person to talk about. This is sort of like the proof by example or by construction, right? We want to overall there we want to prove an existence. We want to prove the existence of three mutual friends or existence of three mutual strangers. So it's a useful step to either construct one, or in this case we're actually not doing much for construction. We're just taking an arbitrary x. But that will be enough for this problem. Okay, so let me draw a little circle for P. And it might have some friends, and it might have some strangers. Okay, how many of these lines coming out of P are there? 5, exactly, because there's 6 people total. P is one of them, so there are 5 people over here. Okay, so turns out useful case strategy is to say either P has at least 3 friends, or it has less than 3 friends. Right? Either there are 3 solid lines like I've drawn here, or there are at least 3, or there are at most 2 solid lines. Okay, let's think about this first case. P has at least 3 friends. Let's give them a name. Q, R, and S. So that's sort of a general picture. Now we're assuming P has 3 solid lines to 3 people, Q, R, and S. Okay, this is not yet a triangle. We haven't solved the problem yet. But if we break into more cases, we'll be able to. Okay, so case 1A is going to be sum 2 of Q, R, and S are friends.
방금 본 출발점의 핵심은 P를 특별한 사람으로 고른 게 아니라는 데 있습니다. 아무나 한 명 잡아도 됩니다. 6명 중 P를 빼면 5명이 남죠. 그 5명과 P 사이는 각각 친구거나 낯선 사이입니다. 그런데 5을 두 종류로 나누면 적어도 한 종류는 3명 이상일 수밖에 없습니다. 비둘기집 원리죠. 그래서 먼저 이렇게 나눕니다. P에게 친구가 적어도 3명 있는가? 친구가 셋이라면 그 3명을 Q, R, 그리고 S라고 부르죠. 이제 남은 건 그 3명 Q, R, 그리고 S 사이가 어떤 모양인지 보는 일입니다.
Okay, suppose, for example, Q and S are friends. Have I found a triangle? Yes. P, Q, and S are mutual friends if this edge is here. Or if this edge is here, then these 3 people are 3 mutual friends. Or if this edge is here, these 3 people are mutual friends. If there's any edge in here that I can draw, any solid line between Q, R, and S, then those 2 people plus P form 3 mutual friends. Okay, so that case is actually easy. Great. Then P plus those 2 people are 3 mutual friends. Okay, which was situation 1 up here. There's always either 3 mutual friends or 3 mutual strangers. Okay, so now we need to think about the other cases. Let's go over here. We found one case that was easy, but there's case 1b, which is maybe there aren't 2 mutual friends, and there's case 2, where P does not have at least 3 friends. Okay, but it turns out all of these cases will be easy. So let's do case 1b. Now, I get to sort of freely choose what case 1 was, and I get to freely choose what case 1a was. Because whenever I split into cases, I get to choose my proposition C to be anything I want. So this was C in the first case, this was C in the second case. But generally, if you're doing proof by 2 cases, you have no choice at this point. So case 1a was whatever. Case 1b has to be the negation of this. Okay, so case 1b literally is not sum 2 of Q, R, S are friends. But if you think about that for a little bit, this is saying Q, R, and S. Let me write this in a couple of steps. No 2 of Q, R, and S are friends. But that's the same thing as saying Q, R, and S are mutual strangers.
이 경우는 P와 이미 친구인 Q, R, 그리고 S를 확보한 다음 그 셋 사이를 들여다보는 단계입니다. Q, R, 그리고 S 중 어느 2명이라도 서로 친구라면 그 둘은 P와도 친구니까 곧바로 친구 3명이 됩니다. 반대로 셋 사이에 친구 관계가 하나도 없다면 셋 쌍 모두 낯선 사이라서 Q, R, 그리고 S 자체가 서로 낯선 3명이 되죠. 여기서 흔한 착각이 하나 있어요. 친구 삼각형을 찾으려면 변 3개를 새로 확인해야 한다라고 생각하기 쉽거든요. 그런데 P에서 Q, R, 그리고 S로 가는 3변은 이미 친구로 확보되어 있습니다. 그래서 셋 내부에 선이 하나만 있으면 친구 삼각형, 내부에 선이 하나도 없으면 낯선 삼각형입니다. 이제 남은 건 P에게 친구가 3명 미만인 경우인데 이때는 친구와 낯선 사이의 역할만 바꿔서 같은 논리를 다시 씁니다.
Okay, we're using this fact of this assumption that every 2 people are either friends or strangers. Always one or the other. So if there's no solid line over here, then all of these are dashed lines. So all 3 of these are mutual strangers, and there we found our triangle of strangers. Okay? So it turns out case 1a and case 1b are actually just as easy, just sort of reversed. So this was situation 2. So either we got 3 mutual friends or we got 3 mutual strangers, but we're still inside case 1. We just finished case 1. Now we need to think about case 2. So I'm going to unindent here and go to case 2. Case 2, again, has to be exactly the opposite of this. So P does not have at least 3 friends. By number of people being an integer, this is saying P has at most 2 friends. Okay, if it doesn't have at least 3, it's at most 2, because the number of friends is always an integer. Okay, great. So the case 2 is a negation of case 1. And it turns out that is also kind of easy for a symmetric reason. Remember, there are 6 people total. So there's P and 5 others. So how many strangers is P with? Or how many people is P a stranger to? Well, it's at least all the others, 5 minus 2. Because at most 2 of them are friends. The remainder have to be strangers. And so this is 3. So P having at most 2 friends is the same thing as P having at least 3 strangers, because there are 5 other people total. 2 plus 3 is 5. So case 2 is P has at least 3 strangers. Case 1 was P has at least 3 friends. These are almost the same. I just have to flip friends versus strangers. So the way I would write this in a proof is this is symmetric to case 1, swapping friends versus strangers, and of course case 1 or situation 1 with situation 2. Okay, so case 2 would be P has at least 3 strangers, Q, R, and S. Case 1a is that some two of Q, R, and S are strangers. Then we conclude that P plus those two are three mutual strangers, which is situation 2. Or case 2b would be no two of Q, R, S are strangers. In other words, Q, R, S are mutual friends, and then we're in situation 1. So case 2 works just like case 1, just swapping the words friends and strangers because they didn't really have any meaning. They were just words. Cool. So in all cases, we prove the desired result, either situation 1 or situation 2 happens. This is a particular case of something called Ramsey theory.
여기서 먼저 짚어둘 점은 적어도 셋은 아니다가 곧 많아야 둘이라는 정수 조건입니다. P에게 친구가 적어도 셋이 아니라면 친구는 없거나 1명, 많아야 2명 뿐이죠. 그런데 P 밖에는 모두 5명이 있으니 친구가 많아야 2이면 낯선 사람은 적어도 3명입니다. 그러면 똑같은 논리를 친구와 낯선 사이만 바꿔 그대로 적용합니다. 그 세 낯선 사람 사이에 낯선 관계가 하나라도 있으면 P와 함께 낯선 삼각형이 됩니다. 그런 관계가 하나도 없으면 그 셋은 서로 친구라서 친구 삼각형이 되죠. 두 경우가 모든 가능성을 빠짐없이 다뤘으니 증명이 끝났습니다. 그리고 이렇게 얻은 결과는 단순한 퍼즐이 아니라 램지수라는 이름으로 일반화됩니다.
What we've just found is that something called R of 3, 3 is at most 6. In general, R of F, S is the number of people you need in order to guarantee that there's at least F friends or at least S strangers. So we just did at least 3 friends or at least 3 strangers. We showed that 6 people was enough. It turns out 6 people is exactly the right number. You need 6 people in order to guarantee at least 3 friends or 3 strangers. If you wanted to guarantee 4 friends or 4 strangers, turns out you need 18 people. If you want to guarantee 5 friends or 5 strangers, turns out you need somewhere between 43 and 48 people. But we don't know how many. So while this problem was relatively easy, 3 friends or 3 strangers, 5 friends and 5 strangers already is an unsolved mathematical problem. So that's kind of cool and crazy how easily you get to very difficult problems. Of course, people try to compute larger numbers too, but we don't have tight bounds generally.
방금 증명한 말을 정확히 적으면 R33은 6 이하입니다. 6명이면 서로 친구인 3명 또는 서로 낯선 3명이 반드시 보장된다는 뜻이죠. 여기서 보장은 어떤 모임이든 예외가 없다는 뜻입니다. 예쁜 예시 하나를 찾았다는 게 아니라요. 실제로 R33은 정확히 6이고 4명씩 보장하려면 R44는 18까지 커집니다. 여기서 한 가지 더, R55는 43과 46 사이라는 것만 알 뿐 정확한 값은 아직 아무도 모릅니다. 이렇게 경우로 나누는 방법은 강력하지만 두 경우로 부족할 때는 더 조심해야 합니다. 여러 조건이 전체 가능성을 빠짐없이 다루는지 확인해야 하거든요.
Okay, I want to say one more thing about proof by cases, which is what if we want more than 2 cases? So more generally, proof by K cases So instead of just C or not C, let's suppose we have a bunch of propositions C1 through CK, and let's suppose that this is a tautology. Favorite word for the day. So suppose that it's always the case C1 or C2 or ... or CK. One of these things is always true. Then we can follow this template. Which is, suppose we want to prove a theorem that some proposition P is true. Then we'll say proof by cases. And there's K of them, so I'm just going to write it generically. In case I is that CI is true. In other words, we get to assume CI is true. And then what we need to do is prove that P is true in that scenario. And P is true because reasons. And then here it's especially important to say that the cases are exhaustive because reasons. And exhaustive here just means that C1 or C2 or up to CK is a tautology. Okay, so you need to prove that C1 or up ... or CK is always true. That's the meaning of the cases being exhaustive. So there's sort of two parts. One is to prove that each case is okay. The other is to prove that those cases cover everything. Okay, so
K계의 경우로 하는 증명은 두 경우 증명을 자연스럽게 늘린 것입니다. 핵심 조건은 C1 또는 C2 쭉 가서 CK 중 적어도 하나는 늘 참이어야 한다라는 것입니다. 이걸 두고 경우들이 빠짐없다고 말합니다. 그런데 각 경우에서 결론을 증명하는 것만으로는 부족합니다. 예를 들어 정수를 다루면서 양수인 경우와 음수인 경우만 증명하면 0을 빠뜨린 거라 전체 증명이 아닙니다. 그래서 좋은 경우 나누기는 두 가지 일을 같이 해야 합니다. 각 경우 안에서 결론을 증명하고 그 경우들이 모든 가능성을 빠짐없이 다룬다는 것도 증명해야 하죠. 이 원칙이 왜 그렇게 중요한지는 사색정리 이야기에서 선명하게 드러납니다.
I won't show an example of K cases here. We'll see them in recitation and so on. But I will tell you a story about one famous proof by cases, which is the four-color theorem. I'll illustrate the four-color theorem with an example. So here's a map of the United States. And I've colored all the states, all the regions of this map with four different colors, red, green, blue, yellow, in such a way that if you have two regions that share a positive length boundary, then this color A is different from this color B. Okay, it has to be not equal. Otherwise, if you had two red regions next to each other, it would be hard to see the boundary. So the colors illustrate the boundaries between all the regions. Four colors seems to be enough for this map. It's also enough for this map of all the countries. Is it true for all the maps? Turns out, yes. This is called, for a long time, it's called the four-color conjecture, and then it became the four-color theorem at some date. So four-color theorem says you can color the regions of any planar map with four colors so that neighboring regions get different colors. This was first observed and sort of conjectured in 1852 by a guy named Guthrie, who was a student of Demaine. Demaine, I think his name will come up in a moment, famous logician. He actually invented induction, one of the first people to, he invented the term mathematical induction at the very least, and really sort of made it more formal. So a student of him, Guthrie, said, hey, I took all the counties of England, and it turned out I only needed four colors. Is this a theorem? And he asked indirectly De Morgan, and De Morgan said, hey, seems cool. I don't know, maybe. Then the following year, 1853, another mathematician named Kemp proved the theorem. But proved should be in quotes because 11 years later, 1864, Haywood found a bug in that proof. Turns out there were a lot of cases in this proof, and the cases were not exhaustive. So it wasn't done. Then, 15 years later, 1880, Tate proved the theorem. Then, 11 years later, Peterson found a bug in that proof. Again, not all the cases were exhaustive. Then, 85 years later, 1976, Apple and Haken, or maybe it's Appel, I'm not sure, proved the theorem. And I think most people consider this an actual proof, but it's a little tricky. Just to give you a sense, this is where sort of I started hearing about the problem. I wasn't alive in 1976, but I heard about it later on. There are 1,834 cases in this proof. They occupy about a 400-page printout from a computer program. And so this is one of the first mathematical proofs that used a computer to assist in checking all the cases. Because there's so many, 1,834, it's hard to do that by hand and be sure that you didn't make a mistake. So the computer proof, to me, is a little bit more sound. Also apparently checked by hand by Haken's daughter. Then, 5 years later, Schmidt found what you could interpret as a bug in this proof, let's say an omission or something, but a missing situation. And then over the next 8 years, Apple and Haken fixed all the bugs they could find, that one and some other sort of wording issues and so on, and they published it in a book. But a book isn't refereed, so I don't know how many people have read that book. Seems like this proof is maybe correct. It's been many years and no one has found a bug. A little bit later, though, 1996, Robertson, Sanders, Seymour, and Thomas, some of the top graph theorists in the world, found a simpler proof. That proof only has 633 cases. So that's a lot less, maybe 3 times fewer cases. And also the length of the paper is shorter, maybe 10 times shorter. So that's progress. But is that proof true? It also used a computer to check the cases. Finally, in 2005, Werner and Gonthier developed a fully computer checkable proof using a system called Coq, where you write down every step in the proof, and then the computer just has to check that every mathematical derivation, like all the derivations we saw last class, modus ponens and all those things, are correct. This program has
사색 정리의 교훈은 경우를 많이 나누면 언젠가 끝난다가 아닙니다. 나눈 경우가 빠짐없이 전부인지를 증명해야 한다입니다. 지도 색칠 문제에서는 맞닿은 두 지역이 같은 색이면 경계가 구분되지 않습니다. 그래서 서로 이웃한 지역은 다른 색을 받아야 하죠. 정리는 어떤 평면 지도든 4가지 색이면 충분하다고 말합니다. 그런데 이 명제의 증명은 단순한 송해산만으로 끝나지 않았습니다. 역사적으로 캠페의 증명처럼 그럴듯해 보였지만 빠진 경우가 드러난 시도도 있었고, 이후 아펠과 하켄의 컴퓨터 보조 증명, 더 엄밀한 검증, 그리고 코크 같은 형식 검증으로 신뢰를 쌓아갔습니다. 그래서 이 이야기는 컴퓨터가 등장해 멋지다는 쪽보다 빠뜨린 경우 하나가 전체 증명을 무너뜨릴 수 있다라는 경고로 읽는 편이 정확합니다. 오늘의 모델을 한 줄로 정리해 볼게요. 경우로 나누는 증명은 나눈 경우가 모든 가능성을 빠짐없이 다루고 각 경우가 같은 결론에 이를 때만 성립합니다. 램지 증명에서는 이 구조가 깔끔했죠. 친구냐, 낯선 사이냐가 둘 중 하나고 5이라는 수가 셋대 둘의 불균형을 강제했기 때문이죠. 여러 경우로 늘려도 같은 논리가 그대로 확장됩니다. 다만 사색 정리는 경우가 많아지면 빠짐이 없다는 걸 빈틈없이 보이지 않는 한 실수를 놓칠 수 있다고 경고합니다. 다음에는 이 경우 나누기 감각이 여러 갈래로 갈라지는 귀납법 증명에서 어떻게 힘을 발휘하는지 보겠습니다. 증명을 한번 써두고 무한히 많은 경우를 한꺼번에 끝낼 수 있다면 어떨까요? 그게 바로 귀납법입니다. 먼저 pn이 무슨 뜻인지부터 짚을게요. pn은 자연수 n에 따라 참인지 거짓인지가 갈리는 명제입니다. 예를 들어 0부터 n까지 다 더하면 n 곱하기 n 더하기 1 나누기 2가 된다 같은 거죠. 보통 귀납법은 먼저 시작 경우를 증명하고 한 경우가 참이면 다음 경우도 참임을 보입니다. 그런데 오늘 우리가 궁금한 건 이겁니다. 귀납법이 되느냐가 아니라 다음 경우를 증명할 때 무엇을 가정해도 되느냐죠. 바로 이 질문이 보통 귀납법을 강한 귀납법으로 바꿉니다. 이제 그 출발점인 귀납법의 공리부터 함께 정리해 봅시다.
Stood many years of scrutiny, so we all believe that it's correct. And so the fact that you can write the entire proof in this proof language suggests that this really is a true theorem now. Thankfully, there won't be more missing cases. I believe that is just an implementation of the Robertson proof. So that one withstood scrutiny. But it's very tedious to write these proofs, and so for the four-color theorem, it's worth it, I would say. All right, so that's just an example of, in general, proofs by cases can involve a zillion cases. It's very annoying, but sometimes that's the best thing we know how to do. Maybe we'll come up with a simpler four-color theorem proof at some point, but best we know so far has hundreds of cases. All right, let's go back to induction. First, I want to review induction a little bit, and then we will get a stronger form of it. So I'm going to call this the induction axiom. This is what we talked about last class. We didn't call it an axiom, and in some setups it is an axiom. We're going to take it as one, something that we just assume is true. Although, as Zach mentioned, in modern times, you usually prove this using the definition of the natural numbers. But I'll just take it as something is true. So for any predicate P of n over the natural numbers, if on the one hand P of 0 is true, and on the other hand, P of n implies P of n plus 1 for all natural numbers n, then P of n is true for all natural numbers n. Okay, this is the magic of induction. You should use this probably in every problem you solve. Not every problem, but extremely powerful tool. We're going to use it all the time throughout this class. I want to give you a visual way of thinking about what's going on with induction, which I call block diagrams. I'm going to think of a block, like a little box here, that takes as input, think of it as a procedure. You give it some true propositions on the left, and it produces.
방금 두 조건을 다시 봤죠. 이 두 가지면 충분하다는 겁니다. 하나, 시작 경우 P0을 증명한다. 둘, 모든 n에 대해 Pn이 참이면 Pn 더하기 1도 참임을 증명한다. 이 둘만 있으면 모든 자연수 n에서 Pn이 참이라고 결론 지을 수 있습니다. 여기서 처음에 헷갈리는 게 하나 있어요. Pn을 명제 하나로 보면 안 됩니다. Pn은 사실 명제들의 모음입니다. n이 0인 경우, 1인 경우, 2인 경우가 각각 따로 있죠. 이어서 이 증명들을 그림으로 옮겨 공리가 어떻게 맞물리는지 봅시다.
A true proposition on the right. Okay, or you could think of it as if I give you some proofs of these propositions, then this block will give you a proof of a proposition on the right. Okay, so what's going on with induction is we're given two of these blocks, these two. So you can think of part 1, P of 0 is true, as a block that has no input. So this is what we normally call the base case. So it doesn't need to assume anything, and it just produces for you a proof that P of 0 is true. Okay, and the second part here, the induction step, says that if you can prove P of n is true, and you plug it into the induction step, then it will give you a proof that P of n plus 1 is true. So a bunch of examples of this last time. We assume P of n, and we use that to prove P of n plus 1. Okay? Now, the cool thing about blocks is you can just chain them together. So if we chain, the only block we can place first is this base case, because it doesn't need anything to get started. So we start with the base case argument. That produces P of 0. Now we plug this into the step. This step has to work for all n. So in particular, it works for n equals 0. And so we plug that into the step, and we get P of 1. We plug P of 1 into the step, so n equals 1. Then we get P of n plus 1, namely P of 2. And we plug that into the step, and we get P of 3, and so on. Okay, so this just gives you some intuition for if I can build an argument for why P of 0 is true, and I can build an argument for why if P of n is true, then P of n plus 1 is also true, then I can just repeat that argument over and over with different n, increasing n by 1 each time, and I can use that to prove that all the P of n's are true. Okay, this is like visual intuition for why this works. Of course, we're not going to actually prove P of n is true for all n, but should be pretty intuitive from that. Or, more abstractly, you can actually think of induction itself as one of these blocks. Let me use another color. So we have, on the one hand, a block base, which produces P of 0. And we have an induction step, which given P of n, produces P of n plus 1. So I'm going to think of this as a thing that's true, and this as a thing that's true. And then what induction gives me, induction is a block that given these two facts, if you can prove each of these things, then it gives me a new fact, which is for all natural numbers n.
증명을 블록 두 종류로 나눠 봤습니다. 시작 블록은 입력이 없습니다. 그냥 P형을 내놓죠. 단계 블록은 Pn 증명을 넣으면 Pn 더하기 1 증명을 내놓습니다. 이게 모든 n에서 통하니까 0에 쓰고 다음 1에 다음 2에 끝없이 이어 쓸 수 있죠. 예를 들어 Pn이 2의 n제곱은 n 더하기 1 이상이다 라고 해봅시다. 시작 블록은 n이 0인 경우 이걸 증명하고 단계 블록은 n에서 참이면 n 더하기 1에서도 참이 되는 이유를 보여줍니다. 이어서 이 블록들을 하나의 큰 블록으로 묶어봅니다.
P of n is true. Okay, so that's sort of the, instead of having to draw out this infinite length path, induction just does it all at once. It says, oh, I know I can chain these all together forever, therefore P of n is true for all n. Okay, I don't know if that helps, but it's another visual way of thinking about induction. Let's all right. Let me tell you another equivalent formulation of induction, which I prefer. Starts out the same. Suppose P of 0 is true. The induction step I'm going to phrase slightly differently, almost the same. For all n at least 1, P of n minus 1 implies P of n. Then for all natural numbers, P of n. So the first and last lines are the same. We're going to assume P of 0 is true. We're going to conclude P of n is true for all natural numbers. Here, we started at 0, and we wanted to show that P of n implies P of n plus 1. Over here, we're starting at 1, and we're proving that P of n minus 1 implies P of n. These are exactly the same things. I've just shifted the indices by 1. So these are identical statements, or equivalent statements. I like this version. In particular, it will lead into strong induction. But I like this version as a computer scientist because I always want to think about, well, I want to prove P of n, not P of n plus 1. It's confusing to think about proving P of n plus 1. I always want to prove P of n. When n equals 0, OK, that's my base case. I prove that specially. When n is at least 1, I'm not in the base case. And I get to assume that P of n minus 1 is true. You can think of this like a computer program. Think of proving P of n is like running a computation f of n, or P of n, and I get to recursively call P of n minus 1 in order to compute P of n. n is given to me. This is the one I want to solve. If n is 0, then I solve it one way. If n is bigger than 0, or at least 1, then I recursively call P of n minus 1, or depend on that proof, and use it to prove P of n. Okay? But you can use either one, whichever is more comfortable to you.
그 큰 블록의 핵심은 이겁니다. 무한한 그림을 유한한 규칙 하나로 바꾸는 거죠. P0에서 P1로, P1에서 P2로 끝없이 손으로 잇는 대신에요. 공리를 보면 이렇습니다. 그 두 재료만 있으면 모든 자연수 n에서 Pn이라는 결론이 정당해집니다. 이게 중요한 이유는 증명은 무한히 많은 경우를 다뤄도 그 자체는 유한해야 하기 때문입니다. 이제 같은 규칙을 한 칸 옮겨봅니다. Pn이면 Pn 더하기 1 대신 Pn 빼기 1이면 Pn으로요. 이어서 인덱스를 한 칸 옮긴 모습을 함께 보겠습니다.
But really, you should use neither, and you should use this stronger form called strong induction. So let's do that. Strong induction just gives you more to work with. So it's in some sense more powerful. Logically, it's identical to induction. You can actually prove it using induction, and we'll do that. Let me first state the theorem. So if any natural number this is true, then for any natural number, P of n is true. Okay, let me bring this one down to compare. First thing maybe to notice is that it doesn't seem to be a base case here, which is a little weird. It's just one condition, then this. Let's compare the steps first of all. Or I guess let's think about the case. This has to be true for all n. If we think about when n equals 0, that's the missing base case. What this is actually saying is p0 up to p minus 1 implies p of 0. Okay, so this is kind of weird notation. I'm abusing the ... a little bit here. And for when n equals 1, this is p of 0. When n equals 2, this is p of 0 and p of 1. When n equals 3, I mean, for larger n, it's very clear what this ... means. But when n equals 0, it's confusing. So I need to specify this is defined to be true for n equals 0. Okay, so for n equals 0, what you have to do is prove that true implies p of 0. In other words, p of 0 must be true in all cases. Okay, so there's, but then for larger n, what this is saying is not only do I get to assume p of n minus 1, but I get to assume all the p of i's before p of n. So I would normally say p of I is true for all I less than n. This is what I get to assume. That's probably actually a better way to state this thing.
인덱스를 한 칸 옮긴 이 형태는 보통 귀납법과 똑같은 말입니다. 다만 목표 n을 기준으로 본 거죠. 먼저 P형을 증명하고 n이 1 이상일 때 Pn-1이면 Pn임을 증명합니다. 그러면 모든 자연수에서 Pn이 참이죠. 수학적으로 달라진 건 없습니다. 그런데 보는 관점이 바뀝니다. Pn을 증명할 때 앞에 어떤 사실을 써도 되지? 하고 묻게 되거든요. 목표가 이미 Pn이라 실제 증명에서 이게 더 편할 때가 많습니다. 여기서 한 가지 짚어둘 게 있어요. n이 0이면 그보다 작은 자연수가 없습니다. 그래서 앞에 모든 경우를 가정한다라는 말이 아무것도 가정하지 않는다는 뜻이 됩니다. 이제 가정할 수 있는 게 바로 앞 하나가 아니라 n보다 작은 모든 pi로 넓어집니다.
So with regular induction here, I got to assume that the previous p of n minus 1 was true, and I needed to use that to prove that p of n is true. But actually, if you look at this chain, like by the time I'm proving p of 3, I've already proved all the smaller pi's. So why not assume that? With strong induction, I get to assume that. In order to prove p of n, I get to assume all the pi's where I is less than m. Okay, now when n equals 0, I don't get to assume anything because there are no smaller i's. But when I get to p of 5, I get to assume p0, p4, p0, p1, p2, p3, p4. So I get to assume more, so this only makes my proof easier. Okay. To be clear, this is usually proved in cases. Normally you need to check 0 specially. That might be a base case. Maybe you have to check 1 specially. It depends on your implication argument. Often this implication assumes that n is at least something, and then you have to prove all the smaller n's to be true specially. But we'll get to examples in a moment. What I'd like to do first is actually prove that strong induction is true. This is not something you would repeat in your homework. You should just assume strong induction is true. But I think it's instructive to see why it's true as yet another example of induction. Okay, so we're going to use regular induction, this version, or actually I think this version, the induction axiom, to prove strong induction. Okay, now this is a situation where we need to define a particular induction hypothesis. This is not the obvious one. And this is not at all obvious, but I'm going to define IH of n to be this P of 0 and P of n minus 1. In other words, for all I less than n, P of I. I like that better because it works even when n is 0, because there are no i's less than 0, so that's just true when n is 0. Okay, so this is the thing I want to prove for all n. And how do we do it? Well, as usual with an induction, we have a base case. Base case is IH of 0. So IH of 0 is actually literally just true, because we defined it to be that way. We said when n equals 0, this ... is true. Or you could say this is saying for all I less.
이렇게 강한 귀납법까지 왔습니다. 핵심은 가정의 폭입니다. Pn을 증명할 때 n보다 작은 모든 i에 대해 pi를 가정해도 됩니다. 그러고 Pn을 증명하죠. n이 0이면 더 작은 i가 없어서 가정 없는 시작 경우처럼 됩니다. n이 5라면 P0, P1, P2, P3, 그리고 P4를 전부 마음껏 써도 되고요. 이게 도움이 되는 이유는 많은 증명이 바로 앞 Pn-1 하나에만 기대서는 풀리지 않기 때문입니다. 예를 들어 1보다 큰 정수가 소수들의 곱으로 쪼개진다라는 걸 증명할 때 더 작은 약수를 쓰는데 그게 n-1보다 한참 작을 수 있거든요. 흔한 오해 하나, 강하다는 말이 더 많은 정리를 증명한다는 뜻은 아닙니다. 논리적으로는 보통 귀납법과 똑같고 다만 증명을 더 편하게 쓰게 해주는 형식이죠. 오늘 머리에 남길 핵심은 이겁니다. 보통 귀납법은 경우를 하나씩 바로 앞 경우에 기대 이어갑니다. 강한 귀납법은 지금 경우를 증명할 때 앞에 모든 경우를 가져다 씁니다. 더 많은 정리를 증명한다는 뜻에서 강한 건 아닙니다. 둘은 똑같은 정리를 증명하죠. 다만 많은 증명이 바로 앞 경우 하나보다 더 많은 걸 필요로 합니다. 그래서 실전에서는 이쪽이 더 편합니다. 다음 시간에는 강한 귀납법이 보통 귀납법에서 따라 나온다는 걸 증명해 봅니다. 그러면 강한 귀납법이 새로운 수수께끼가 아니라 믿고 쓰는 도구가 됩니다. 강한 귀납법을 처음 보면 보통 귀납법보다 훨씬 많은 걸 가정해도 된다라는 점이 좀 수상하게 느껴집니다. 한 단계를 증명하는데 그 앞의 결과를 전부 가져다 써도 된다니 거의 반칙처럼 보이죠. 그런데 오늘 보면 이게 전혀 새로운 규칙이 아니라 보통 귀납법을 살짝 다르게 포장한 것뿐입니다. 출발하기 전에 준비물 2개만 짚을게요. Pn은 숫자 n에 붙은 성질입니다. n마다 참이거나 거짓이 갈리는 명제죠. 그리고 논리곱은 여러 명제를 그리고로 이어붙인 것이라 한 조각이라도 거짓이면 전체가 거짓입니다. 오늘의 핵심 동작은 앞선 명제 여러 개를 하나로 묶는 겁니다. P0부터 Pn-1까지를 한 명제로 묶어서 귀납 가정 n이라고 부릅니다. 이 묶음이 분명해지면 강한 귀납법은 그냥 더 큰 가정을 쓰는 보통 귀납법이 됩니다. 먼저 이 묶음이 n이 0일 때 어떻게 시작하는지부터 같이 봅시다.
Less than 0, where I is a natural number, but there are no natural numbers less than 0. So this is like saying if false, then something, and that's just always true. So this is by definition IH of 0 is true. Great. Easy base case. As usual. What's the induction step look like? I get to choose. I could either assume IH of n minus 1 and prove IH of n, or I'm going to assume IH of n and prove IH of n plus 1. So we want to show IH of n plus 1, assuming IH of n.
방금 첫 장면에서 가장 헷갈리는 지점이 나왔습니다. 귀납 가정 0은 P0을 말하는 게 아닙니다. 귀납 가정 0은 0보다 작은 모든 자연수 i에 대해 pi라는 뜻이거든요. 그런데 0보다 작은 자연수는 하나도 없습니다. 그래서 이 논리곱은 비어있고 거짓일 항이 하나도 없으니 자동으로 참이 됩니다. 아직 어떤 p도 증명하지 않았지만 어겨야 할 항도 없으니 통과인 거죠. 정확히 말하면 이건 Pn이 아니라 새 명제 귀납 가정 n의 시작 경우를 채워준 겁니다. 그럼 이제 본격적인 단계로 넘어갑니다. 앞에 결과가 다 있을 때 빠진 다음 하나 pn을 어떻게 붙이느냐죠.
Cool. So the key thing is we get to assume this is true. The strong induction says if this, then this. So we're assuming the if part. We're assuming that if this implication and this thing here is exactly IH of n. Right? So this says IH of n implies P of n. So we know IH of n implies P of n. That's what we get to assume in our theorem statement here. And we just assume that IH of n is true. Therefore, P of n is true. Okay, but P of n was not what we wanted to prove. We wanted to prove IH of n plus 1. So what is IH of n plus 1? Let's just expand out this definition here. It is P of 0 or ... or P of n minus 1 or P of n. Because I've incremented n by 1, this no longer ends at P of n minus 1, it now ends at P of n. Okay, but this is almost what we had before. This is the induction hypothesis of n, that's this part, or P of n. Right, that's just formula manipulation. And this we assumed is true, IH of n is true, and P of n we just proved is true. Sorry, I wrote or here, but I meant and everywhere. This is and, see, even professors get the V's and wedges upside down. So I wrote it correctly here. It's the and of P0 up to Pn minus 1. Here we have the and of P0 up to Pn. And so this is IH of n, which we assumed was true by induction, and P of n, which we just proved using one induction step. Therefore, the and is also true. And I believe that's the end of the proof. All right, I did a base case, I did a step. Oh, no, not quite the end, sorry. There's one more step here, which I will put over here.
방금 칠판에서 중요한 건 숫자 계산이 아니라 논리 계산이었습니다. 귀납 가정 n 더하기 1을 펼치면 P0, P1 쭉 가서 Pn까지입니다. 그런데 이건 정확히 귀납 가정 n에 세 명제 Pn 하나를 더한 것과 같습니다. 수업에서도 잠깐 또는이라고 적었다가 그리고로 고치는 장면이 나왔죠. 강한 귀납법은 앞의 경우 중 하나가 아니라 앞의 모든 경우가 다 있어야 하기 때문입니다. 그래서 흔한 실수가 Pn만 증명하면 단계가 끝났다고 보는 겁니다. 정작 목표는 묶음 전체 귀납 가정 n 더하기 1이거든요. 보통 귀납법으로 귀납 가정 n을 모든 n에서 증명하고 나면 마무리로 한 가지가 남습니다. 그 묶음에서 원래 Pn을 꺼내는 일이죠.
It's a good illustration in not skipping steps. What did we actually prove? By induction, we proved induction hypothesis of n is true for all n. So by induction, like the regular old induction axiom, for all natural numbers n, induction hypothesis of n is true. Induction hypothesis of n is this thing, but that's not what we wanted to prove. We wanted to prove P of n is true for all n. But I can do some manipulation to make that what I want. So this is like saying for all n, let's see, actually, probably this is nicer. For all natural numbers, IH of n plus 1 is true. Okay, this is a shift. It's actually a weaker shift. This includes IH of 0. This should not be greater than or equal to. This should be an element of. This includes 0. This doesn't. This starts at 1 and it goes upwards. But this is nice. So this implies this, right? This is what we've shown. This is a weaker statement because I just threw away IH of 0. IH of 0 wasn't interesting anyway. IH of 1 includes inside of it, so it's an and of a bunch of things, but then the last term is P of n. Right? That's, if I take IH of n plus 1, the last term in it is P of n. So it's also anded, but if the and is true, then every term is true. And so therefore, P of n is true for all n. Okay, so this was a final cleanup. After we did induction, we didn't quite get the statement we wanted because we used a different induction hypothesis than just P. And then we needed to show that that implied P of n for all n. Okay, but it works. Cool. So now there should be no question about why strong induction is true, assuming you believe this proof. You can draw a diagram.
방금 장면에서 자주 건너뛰는 부분이 바로 이 정리 단계인데 증명이 엄밀해지는 이유가 여기 있습니다. 보통 귀납법이 증명해 준 건 모든 n에서 귀납 가정 n이 참이라는 사실입니다. 그런데 우리가 원했던 정리는 모든 n에서 pn이 참이었죠. 둘이 살짝 어긋나 있습니다. 귀납 가정 n 대신 귀납 가정 n 더하기 1로 옮긴 게 바로 이 어긋남을 메워줍니다. 귀납 가정 n 더하기 1은 마지막 항으로 pn을 품고 있기 때문입니다. 예를 들어 귀납 가정 사안에는 P0, P1, P2, 그리고 P3이 들어 있습니다. 그러니 P3이 필요하면 귀납 가정 사안을 들여다보면 됩니다. 다음은 좀 더 그림으로 와닿습니다. 새 Pn 하나를 만들 때 앞에 P 값들을 전부 쓰는데 그래서 강한 귀납법의 의존관계 그림은 한 단계마다 화살표가 여러 개 들어옵니다.
It's a little trickier to do. Maybe I will show you in my handwritten notes here. Here is a block diagram for strong induction. It's harder to draw because you depend on so many things. When I apply the fourth step here, when I want to conclude P of 4, I assume all the previous P's. So P0, P1, P2, P3, they all feed into this box. In the beginning, it's very similar. I apply a step, I get P of 0. Then I apply that P of 0 to a step, I get P of 1. But then, as I proceed, I'm feeding more and more PIs into the step, and it gives me one more PI. Okay, so it's a much more complicated diagram of what's going on under the hood. But from a usage standpoint, it only helps you. When you're trying to prove P of n, you don't just get to assume P of n minus 1, you get to assume all the PIs where I is less than n.
방금 그 블록 그림이 실전에서 어떤 차이가 나는지를 그대로 보여줍니다. 보통 귀납법은 한 칸짜리 사슬처럼 흘러갑니다. P 연기 P1로 이어지고 P1이 P2로 이어지고 이렇게요. 강한 귀납법은 다릅니다. Pn을 증명할 때 이미 증명해둔 P0부터 Pn 빼기 1까지 어느 것이든 끌어다 써도 됩니다. 그렇다고 증명이 느슨해지는 건 아닙니다. 그 앞의 결과들도 방금 우리가 증명한 누적 가정의 논리로 똑같이 보장되어 있기 때문입니다. 이걸 실제 과제에서 쓰려면 깔끔한 작성 틀이 필요합니다. n보다 작은 모든 k에 대해 pk를 가정한다고 적고 작은 시작 경우들을 따로 떼어둔 다음 남은 n을 더 작은 결과들로 처리하는 거죠.
I think I'd like to show you some examples of strong induction, but maybe first I should show you a template for applying induction, strong induction. We'll repeat some of the things that I've said, but I think it's good to have it concrete. So here is a template. Suppose you want to prove something is true for all natural numbers. So for all natural numbers n, P of n is true. Then here's what the proof will look like. By proof by strong induction. So generally, we're assuming P of k for all k less than n. And then we want to show P of n. Okay, or you could shift the numbers by 1, but this is my preferred way of thinking about it. Usually, we prove this by cases, which is the method we just saw. This is why we're pairing proof by cases with strong induction. How do we prove P of n? Well, it might depend. Often, we have some base cases where n is small. So maybe we have to prove P of 0. Maybe we have to prove P of 1. Who knows? let's say up to p of little b are the base cases. Maybe you have to prove those specially for some reason. Okay, then we do an induction step. So I'll say by cases here. Induction step, we get to assume n is bigger than b, because we just proved 0 up to b manually. And then we need to prove, in those scenarios, p of n is true, because reasons. Okay, but the big thing here is we get to assume in these reasons, we get to use p0, p1, up to p n minus 1. Okay, so that's the big win. And in the base cases, you also get to assume this, but for example, when you're proving p0, you don't really get to assume anything, because there are no smaller pi's. So often you have to do these specially because the induction step assumes somehow that n is bigger than 0. Sometimes you get lucky, you just need the induction step, but usually you need base cases. Let's see some examples, and this will become much clearer. So let's play.
그리고 방금 본 게 오늘의 보상, 바로 쓰는 템플릿입니다. 모든 자연수 n에서 pn을 증명하려면 먼저 강한 귀납법으로 증명한다고 적습니다. 그 다음 n보다 작은 모든 k에 대해 pk를 가정하고 그걸로 pn을 증명하면 됩니다. 시작, 경우가 p0 하나가 아니라 p1까지 또는 더 여러 개일 수 있는 이유가 있습니다. 일반적인 논증이 n이 어느 정도 커야 비로소 통하는 경우가 많거든요. 예를 들어 점화식이 n-1과 n-1을 둘 다 쓰면 p1 하나만으로는 재료가 부족합니다. 그래서 p0과 p1을 둘 다 직접 증명해 둬야 할 수도 있죠. 피해야 할 오해는 강한 귀납법의 가정을 pn 자체의 공짜 근거로 여기는 겁니다. 그 가정은 더 작은 경우만 주고 pn은 거기서 직접 쌓아 올리는 게 우리 몫입니다. 이제 머릿속 모델은 이렇게 잡힙니다. 강한 귀납법은 이전 사실들을 누적해 묶은 것 위에서 도는 보통 귀납법입니다. 귀납 가정에는 n 아래의 모든 사실을 담아두고 단계에서 pn을 더하고 귀납 가정 n 더하기 1이 그렇게 커진 묶음이 됩니다. 실제 증명에서는 n보다 작은 모든 경우 pk를 가정해도 됩니다. 단, 작은 시작 경우들을 분명히 처리해둔 다음에요. 다음에는 예제가 중요해집니다. 이 템플릿은 pn이 바로 앞 pn-1 하나보다 더 많은 것에 기댈 때 비로소 진가가 나오거든요. 블록을 쌓아 올린 더미 하나가 있다라고 해봅시다. 이걸 둘로 쪼개는데 쪼갤 때마다 점수를 받습니다. 점수는 갈라진 두 더미의 크기를 곱한 값이에요. 그러니 어떻게 쪼개느냐, 그 전략이 점수를 좌우할 것 같죠. 본격적으로 보기 전에 용어 3개만 먼저 정해 둡시다. 여기서 자연수는 더미에 쌓인 블록 개수입니다. 전략은 쪼개는 동안 내리는 모든 선택을 말하고요. 블록 전체 개수는 끝까지 변하지 않습니다. 이게 보존이에요. 게임은 모든 더미가 블록 하나씩 남을 때 끝납니다. 크기 1짜리는 더는 둘로 쪼갤 수 없거든요. 그래서 궁금한 건 이겁니다. 우리가 점수를 최대로 키우는 걸까요? 아니면 점수가 이미 정해져 있는 걸까요?
A game called item stacking, or it's really unstacking. So this is unstacking game. So we're going to start with one stack of n, and then a move splits a stack of s bigger than 1 items into 2 stacks with A items in one and B items in the other. And you get to choose these numbers a and b, but you need conservation. So a plus b has to equal s. And we also don't want zero height stacks, so we need a at least 1 and b at least 1. Okay, so you get to choose a and b however you want, so long as there's at least one item in each stack. So let's take a physical example. I got lots of blocks here, but I have no audience, so we're just going to demo this myself. In real life, this was a snow day at MIT, and so we're recording after the fact, so all the students, MIT students have seen it. This is specially for you at OCW. So when we do a move from S, so we have a stack of size S, and we convert it into a stack of size A and a stack of size B, we get A times B points. That's just the definition of the game. A times B points when you split into a stack of size A and a stack of size B.
방금 규칙을 봤죠? 한 번 더 또렷하게 정리해 둘게요. 크기가 S인 더미를 쪼갤 때는 제약이 둘 따릅니다. 양수 A와 B를 고르되 둘을 더하면 원래 크기 S가 돼야 합니다. 그 대가로 받는 점수는 두 조각을 곱한 A 곱하기 B 딱 하나예요. 예를 들어 5를 2와 3으로 가르면 6점이죠. 1과 4로 가르면 4점이고요. 그러니 고르게 가르는 쪽이 이득처럼 보입니다. 여기서 많이들 첫 점수에만 눈이 갑니다. 하지만 게임은 모든 더미가 하나가 될 때까지 계속돼요. 그래서 첫 수만 볼 게 아니라 같은 5짜리 더미를 여러 방식으로 끝까지 쪼개 총점을 비교해 봐야 합니다.
How should I maximize my score in this game? What's the best strategy? The game ends when all your stacks have size 1 because you can't make a move on a stack of one item. It has to be greater than 1 items. So let's try. Here I have a stack of 5 blocks. And one thing, maybe I'll try to split it roughly in the middle. So now, here, I'll rotate this so you can see the block's a little bigger. These are 5 blocks. I split like this. So that's a group of 2 and a group of 3. Product of 2 times 3 is 6. I can do this level of arithmetic. So 6 is our total so far. When I split this one, I get 1 more point. That's 7. When I split this one, doesn't matter how I do it, I get 2 times 1. So that's 2 more points. That's 9. And when I split this group, I get 1 more point. That's 10. Okay, so one approach gives me 10 points. What if another natural strategy, that was like splitting in the middle. Another natural strategy is I just take 1 off each time. So if I take 1 off here, I get 4 points. If I take 1 more off, I get 3 more points. That's 7. 4 plus 3 is 7. I take 1 more off, I get 2 points. That's 9. I take 1 more off, that's 1 point, that's 10. 10 points that way, 10 points the other way as well. Maybe there's a theorem here. Maybe no matter what I do, I get 10 points. Well, that won't be true. But for 5 blocks, I will always get 10 points. For 6 blocks, I will always get, 15, so some more points. It turns out it doesn't matter what strategy you follow, you always get the same number of points for a given initial stack of size n. Let's prove that with strong induction.
방금 2가지로 쪼개봤는데 결과가 묘하죠. 5를 먼저 2와 3으로 가르면 6점, 남은 걸 마저 쪼개며 1, 2, 그리고 1점이 더해져 합이 10입니다. 이번엔 한 칸씩 떼어내 봅니다. 4 더하기, 3 더하기, 2 더하기 1 역시 10이에요. 쪼개는 길은 사뭇 달랐는데 총점은 똑같이 나왔습니다. 그러면 의심이 듭니다. 전략이 총점을 아예 못 바꾸는 거 아닐까요? 예시 2개로는 확신할 수 없죠. 이제 예시를 믿는 걸 멈추고 명제로 못 박을 차례입니다. 주장은 이렇습니다. 시작 크기가 n이면 어떤 전략을 써도 점수는 n 곱하기 n 빼기 1 나누기 2입니다.
Okay, so theorem is for all natural numbers, every strategy for this game, starting with the stack, one stack of n items. Scores. Magic formula is n times n minus 1 over 2. So that's the theorem. And we're going to prove it by strong induction. In sort of the straightforward way. So our induction hypothesis is going to be exactly the theorem statement for a particular n. So I'm going to highlight this statement, everything except the quantifier, and I'll call that P of n. So what I want to prove is for all natural numbers n, P of n is true. And so that's just going to be our induction hypothesis. We're going to plug that into this template here, assume that P of k is true for all k less than n, and then prove P of n is true. So let's just try to do that.
이제 관찰을 정확한 문장으로 바꿉니다. 모든 자연수 n에 대해 n짜리 더미 하나에서 시작한 어떤 전략도 점수가 n 곱하기 n 빼기 1 나누기 2입니다. 이 n 곱하기 n 빼기 1 나누기 2는 삼각수 공식이에요. n에 5를 넣으면 5 곱하기 4 나누기 2, 즉 10이라 두 실험과 딱 맞습니다. 증명은 강한 귀납법으로 합니다. 여기서 Pn은 공식만이 아니라 크기 n에 대한 이 문장 전체를 뜻합니다. 보통 귀납법과 강한 귀납법의 차이가 여기서 중요해집니다. 보통 귀납법은 바로 앞 Pn 빼기 1만 끌었습니다. 강한 귀납법은 n보다 작은 모든 k에 pk를 끌었을 수 있고요. 이게 왜 중요하냐면 n을 처음 쪼개면 a와 b가 나오는데 둘 중 어느 것도 꼭 n 빼기 1인 건 아니거든요.
So what I would normally write here is assume that my theorem is true, assume P of n is true, P of k is true for all k less than n. I would say assume true for all smaller n. Okay, we need to do something with the game. We start with a pile of size n. Let's just think about the first move. First move is something. It takes our pile of size n and it splits it into some piles a and b. So we don't know what it is. We don't know what a and b are, but we can give them a name. Like this has to work no matter what a and b are. But let's say consider first move, which we know we start with a pile of size n, and we produce piles of size a and b. And again, a plus b equals n, and a and b are at least 1. But otherwise, we don't know what a and b are. Okay, so we go down to here. So we now have a pile of size A and we have a pile of size B. Again, we don't know how big they are, but they are smaller than B. So I want to claim we are left with two piles, or we can really think of those as two completely separate games, A and B. We're going to get some points from splitting up A. We're going to get some points from splitting up B. They sum together. But these piles don't really interact from here on. We got A times B points from this first.
증명은 첫 수를 일부러 정하지 않는 데서 출발합니다. n짜리 더미를 a와 b로 가른다고만 둡니다. a 더하기 b는 n이고 둘 다 최소 1이에요. 첫 수를 콕 집지 않으니 고르게 가르든 한 칸만 떼든 모든 전략이 한꺼번에 다뤄집니다. 첫 수를 두고 나면 A 더미와 B 더미에서 남은 작업은 서로 영향을 주지 않습니다. A를 어떻게 쪼개 얻는 점수는 B를 나중에 어떻게 쪼개든 그대로예요. 그러니 첫 쪼개므로 A 곱하기 B점을 받고 그 다음 두 더미가 각자 자기 총점을 따로 쌓습니다. 여기서 강한 귀납법이 들어올 자리가 보입니다. A와 B 둘 다 n보다 엄밀히 작거든요. 그래서 두 더미엔 이미 정리를 쓸 수 있습니다.
Step. We're going to get some points from the pile of size A. We're going to get some points to the pile of size B. How many points do we get? Well, in fact, our induction hypothesis will tell us, because A and B are strictly less than n. Why? Because A plus B equals n, and A and B are at least 1. So there's at least 1 in each of A and B, and so the remainder must be strictly less than n. If there's 1 in A, then there'll be n minus 1 in B. If there's 2 in A, there'll be n minus 2 in B. In all cases, less than n. Okay, because A and B are less than n, they're not necessarily n minus 1, so we couldn't just use regular induction. But they're less than n, and so by strong induction, we know that P of A is true and P of B is true. Okay, we wrote that up here. Assume P of K for all K less than n. So A and B are less than n, so P of A is true and P of B is true. So that means from the pile of size A, we get A times A minus 1 over 2 points. From the A pile, we get B times B minus 1 over 2 points from the B pile. And then, of course, we got A times B points from the first move. And so now we just need to do some algebra and add up all these points. So the total number of points that we get is A times B plus A times A minus 1 over 2 plus B times B minus 1 over 2. These two were by induction. This was the first move. And now let's just put everything over 2. So this is 2 times A times B plus A squared minus A plus B squared minus B all over 2. Okay, and now what do I want to get to? This is supposed to equal n times n minus 1 over 2.
핵심 논리를 따라가 봅시다. A 더하기 B가 n이고 두 조각이 모두 양수니까 A도 B도 n보다 작습니다. 그래서 강한 귀납법을 쓸 수 있어요. A 더미는 A 곱하기 A 빼기 1 나누기 2점을 받습니다. B 더미는 B 곱하기 B 빼기 1 나누기 2점을 받고요. 안에서 무슨 전략을 쓰든 상관없죠. 그러면 총점은 첫 점수 A 곱하기 B에 이 두 작은 게임 점수를 더한 값이 됩니다. 한 가지 조심할 게 있어요. B 더미에서 나오는 점수는 B 곱하기 B 빼기 1 나누기 2지 A로 쓴 다른 식이 아닙니다. 이제 남은 건 계산입니다. 그런데 이 계산이 형식적인 게 아니에요. A 곱하기 B에 A 곱하기 A 빼기 1 나누기 2와 B 곱하기 B 빼기 1 나누기 2를 더한 게 정확히 N 곱하기 N 빼기 1 나누기 2로 모이는지를 보여야 합니다.
And what was n? n was A plus B. So what I'd really like to show here is A plus B times A plus B minus 1 over 2. That's my goal. And what I need to do is fill in the in-between. But this is not too hard because, let's see. I see A times B here and A times B here. I mean, in fact, you can just expand this out and you'll get exactly the same thing here. I think slightly more intuitive is to see, oh, look at this term, and this term. That is A squared plus 2AB plus B squared. That is A plus B squared. And then we have a minus A minus B over 2, but interject a rule in between. We have A plus B squared minus A plus B over 2. And then these two are the same thing. I think that's pretty clear. So cool, we did some algebra, and we just computed what we get out of induction, and then boom, we get the answer n times n minus 1 over 2, and it works. How did we know this is the right answer? I mean, we were just told that by the theorem. Probably you would try this for very small n and make a conjecture. Oh, it seems like it's n times n minus 1 over 2. Let's try to prove it. And when you assume the right thing, the proof just works. And it's kind of magical, and that's strong induction. Again, we need a strong induction here because we needed to assume what we wanted for all smaller n, because we don't know what a and b are. This has to work for all a and b less than n. So luckily strong induction gives us that.
마지막 계산이 가정과 결론을 정확히 이어줍니다. 세 항을 분모 2로 모읍니다. a 곱하기 b는 2ab 나누기 2가 되죠. 그러면 분자는 a 곱하기 a 빼기 1 더하기 2ab 더하기 b 곱하기 b 빼기 1이 됩니다. 펼치면 a 제곱 빼기 a 더하기 2ab 더하기 b 제곱 빼기 b이고요. 제곱 항들은 모이면 a 더하기 b 전체 제곱이 되고 1차 항들은 마이너스 a 더하기 b가 됩니다. 그런데 a 더하기 b가 n이었죠. 그래서 식은 n 제곱 빼기 n 나누기 2가 됩니다. 이건 바로 n 곱하기 n 빼기 1 나누기 2 우리가 원하던 그 값입니다. 왜 맞아떨어지냐면 첫 쪼개은 두 더미 사이를 가로지르는 쌍들을 세고 귀납 가정은 각 더미 안의 쌍들을 세기 때문이에요. 이제 머릿속 그림이 또렷해집니다. 첫 쪼갰 한 번이면 게임이 더 작은 두 게임으로 갈라집니다. 강한 귀납법은 그 작은 크기들에 대해 이미 증명해 둔 걸 그대로 끌어쓰게 해주는 도구죠. n 곱하기 n 빼기 1 나누기 2가 왜 나오는지 또렷해지는 지점이 있어요. 이 값은 블록 n 개에서 나오는 모든 쌍의 개수거든요. 쪼개는 과정 어딘가에서 그 쌍들이 빠짐없이 세워집니다. 전략은 그 곱들이 언제 나타날지 순서만 정할 뿐 최종 총점은 못 바꿉니다. 그래서 처음의 질문, 점수를 키우는 거냐, 정해진 거냐, 답은 이미 정해져 있다는 거였죠. 이 증명 방식은 문제가 바로 앞 경우 하나가 아니라 더 작은 여러 조각으로 갈라질 때마다 쓸모가 있습니다. 팀마다 서로 한 번씩 붙어서 항상 승자와 패자가 갈린다고 해봅시다. 이때 팀들을 한 줄로 세우는데 앞팀이 바로 뒤 팀을 이기도록 세울 수 있을까요? 이게 바로 오늘 같이 풀어볼 질문입니다. 그 전에 두 가지만 먼저 짚고 갈게요. 하나는 라운드 로빈, 모든 팀이 서로 딱 한 번씩 붙고 비기는 경우는 없다는 겁니다. 다른 하나는 우리가 찾는 순서가 옆자리만 이기면 되지 맨 앞 팀이 전체 최강일 필요는 없다는 거죠. 사실 여기엔 함정이 하나 있어요. 가위바위보를 떠올려 보면 이기는 관계가 한 바퀴 돌 수 있거든요. 그래서 제일 센 팀부터 줄 세우는 방식은 아예 안 통할 수도 있습니다. 그런데도 이 순서는 항상 만들 수 있는데 그 핵심 도구가 강한 귀납법이에요. 한 팀만 빼는 게 아니라 남은 팀을 더 작은 그룹으로 갈라서 정리를 다시 적용할 거거든요.
A slightly more complicated version of the same thing. We're going to use strong induction. Don't need any of these. So let's go. That's a problem called beat ordering. I guess somewhat relevant today because it was a Super Bowl, but this is just about any teams of games, n teams in some game. And the setup is that every two teams play a game and there are no ties. One team wins and the other loses. Okay, this is sort of like friends and strangers, where it's either one or the other, but in this case it's asymmetric. They're not both happy or both sad. One's happy and one is sad. Okay, this is what's called a round robin tournament. Most sports are not played this way unless it's a small number of teams because it's a lot of different teams. It's actually n times n plus 1 over 2 games, which is a lot. All right, so what we would like is what's called a beat ordering. This is an ordering of the teams, T1, T2, up to Tn, such that B1 beat, T1, T for teams, T1 beats T2, T2 beat T3, and so on, and Tn minus 1 beats Tn. Okay, let's draw a little example. There's Team Rock, Team Scissors, and Team Paper. Okay, paper beats rock, rock beats scissors, scissors beats paper. Okay, this is a possible outcome in a three-team tournament, there's not necessarily one best team here. There is no best team. But maybe paper and rock play a game, and it happens that paper won. Maybe rock plays against scissors, and it happens rock won, and scissors played against paper, and it happens scissors won. Okay? You can tell why I named the teams this way. Then one way I could order these teams is paper, rock, scissors, because paper beats rock, rock beats scissors. Okay, so this is sort of the input, and this is my goal, is to produce an ordering like this. But I need to do it for n teams, not just for 3. Okay, so let's do strong induction.
방금 봤듯이 우리가 찾는 건 객관적으로 제일 강한 팀이 아닙니다. 가위바위보를 생각해보죠. 보는 바위를 이기고 바위는 가위를, 가위는 다시 보를 이깁니다. 이러면 1등, 2등, 3등 같은 전체 순위는 아예 매겨지지 않죠. 그래서 비트 순서는 조금 약하지만 그래도 짜임새는 있어야 하죠. 줄을 세웠을 때 각 팀이 바로 다음 팀만 이기면 됩니다. 보, 바위, 가위 순서가 그 예입니다. 보가 바위를 이기고 바위가 가위를 이기죠. 맨 앞 보랑 맨 뒤 가위가 직접 붙으면 가위가 이기지만 그건 따지지 않아요. 옆자리 관계만 맞으면 되는 거죠. 정리에 따르면 이런 줄은 늘 존재합니다. 세 팀뿐 아니라 모든 n에 대해 비기지 않는 어떤 대진에서도요.
To prove that the theorem is a beat ordering always exists. Theorem and when I say this always exists, what I really mean is for all n, and then for all tournaments of size n, there exists a beat order. Okay, there exists an ordering of the n teams, such that the first one beat the second one beat the third one, and so on. I should say for all I, ti beat ti plus 1. Okay, so we claim this is true. Proof by strong induction. So we're going to assume that this statement is true, namely this statement is true for smaller n, and then we're going to prove it for n. Okay, let's.
이 정리는 사실 두 겹으로 되어 있어요. 하나는 모든 팀 수 n에 대해, 또 하나는 그 n 개짜리 모든 대진에 대해 순서가 있다는 겁니다. 여기서 강한 귀납법이 나옵니다. 보통 귀납법은 바로 앞한 경우, 그러니까 n-1만 가정하죠. 강한 귀납법은 n보다 작은 모든 크기에서 이미 정리가 참이라고 가정합니다. 이게 왜 필요한지 보죠. 문제가 어떤 크기로 갈라질지 미리 알 수 없기 때문이에요. 예를 들어 한 팀을 골랐더니 그 팀을 이긴 팀이 2, 진 팀이 7일 수도 있습니다. 그럼 크기 2짜리 정리랑 크기 7짜리 정리가 동시에 필요해지죠. 그래서 다음 단계가 자연스럽게 정해집니다. 팀 하나 t를 아무거나 잡고 나머지를 t를 이겼는지 졌는지로 나누는 거예요.
Pick a team, any team, call it t. Then I'm going to split everything with respect to t. So I'm going to define W to be the set of teams that win against t. So this is going to be a set of all teams S where S beat t. So this is 1 versus t. These teams win versus t, or 1 versus t. And L is going to be the set of teams that lose against t. So this is the set of teams S where t beat S. So this is a loss versus t. Then intuitively, what we'd like to do is put the winners first, then put t, then put the losers. I claim that works. Okay, but how do I order the winners? How do I order the losers? Well, by induction. I claim the size of W, this vertical bar means the size of the set, is less than n, and the size of L is less than n, because the size of the winners plus the size of the losers plus 1 equals n. This is a 1. Why? Because every team is either T, or they won against T, or they lost against T. So this is counting all of the teams. There's T itself, the ones that win against T, the ones that lose against T. Together, that is exactly n. Every team is exactly one of these categories. And there's a plus 1 here, and all of these are non-negative. Here, W and L might be 0, but there's this plus 1. That means both W and L are strictly less than n. So the induction applies to them.
이제 고른 팀 T를 기준점으로 삼습니다. 나머지 팀은 딱 두 무리 중 하나에 들어가요. T를 이긴 팀들의 모임을 W, T에게 진 팀들의 모임을 L이라고 부릅시다. 겹치는 팀도 빠지는 팀도 없습니다. 모든 팀이 서로 붙고 비기는 일이 없으니 T와의 승부도 딱 하나로 갈리거든요. 그러면 최종 줄의 모양이 눈에 들어옵니다. 이긴 팀들 W가 앞, 가운데 T, 그리고 진 팀들 L이 뒤죠. W의 팀들은 T로 이어지는 관계가 맞고 T는 L로 이어지는 관계가 맞거든요. 근데 한 가지 짚어둘 점이 있어요. W와 L도 그 안에서 다시 비트 순서를 만들어야 합니다. 그래서 두 무리가 n보다 작은지 봐야 하는데 W의 크기 더하기 L의 크기 더하기 1은 n, 이 식이 바로 그 확인이죠.
So by induction, this thing is true. For any tournament of size W, there exists a beat ordering of W. For every tournament of size L, there exists a beat ordering of L. So we get a beat ordering. We get two of them, really. Let's call it W1, W2, W size of W. This is an ordering of capital W. And we get L1, L2, L size of L as a beat ordering of capital L. And then we concatenate. So we claim W1, W size of W, then T, then L1, L size of L is a beat ordering of all n teams. Again, this is all the teams. All the teams either won against T, or they are T, or they lost against T. And the idea is this part is beat. W1 beats W2, W2 beats W3, and so on by induction, because this is a beat ordering of capital W. Over here, this is a beat ordering of capital L, and so by
W와 L이 n보다 작다는 걸 알았으니 강한 귀납법을 쓸 수 있습니다. 두 무리는 이미 풀린 문제로 봐도 됩니다. W 안에는 각 팀이 다음 팀을 이기는 어떤 순서가 있어요. L 안에도 똑같이 그런 순서가 있죠. 이 순서를 어떻게 찾는지는 몰라도 됩니다. 귀납 가정이 존재한다라고 보장해 주거든요. 여기서 흔히 하는 착각이 하나 있어요. W팀들이 L팀들을 다 이겨야 한다라고 생각하기 쉽죠. 하지만 증명에는 그게 전혀 필요하지 않아요. 줄에서 바로 옆에 붙은 쌍만 보거든요. 그래서 W 순서, T, L 순서를 차례로 이어붙이면 안쪽은 이미 해결되어 있습니다. 이제 T 양옆에 두 이음매만 따지면 됩니다.
By induction, all these are okay. L1 beat L2, L2 beat so on, beat L size of L. The only things we need to check are these two commas. We need to check that W sub big W, W sub size of W beats T, and T beat L1. Why are those true? By our definition of W and L. Everything in W beat T. So this is by the definition of W. We know that all of these beat T. So in particular, this one beat T. And we know by the definition of L all of these teams lost against T. In other words, T beats all of these teams. In particular, T beat L1. And so by combining all these beat statements together, we know that this entire thing is a beat ordering. Each item beats the one right after it. So it's a little more complicated, but again, we're just quite often with strong induction proofs, you apply induction twice. You have some problem with size n, you split it into two parts. In general, you might split it into many parts. Then you recursively solve the two parts or the many parts. As long as they're strictly smaller than n, by induction, we know they work out. By strong induction, we know they work out. You take those solutions and you combine them in some way. Here we concatenated with t in the middle. Over here, we summed them up. We summed up the number of points we got in each one plus the number of points we got in the first step. And in general, you combine them in some way and you prove that it's still that the thing you want to prove holds for size n, and then you get your theorem. So that is the power of strong induction.
이제 증명 전체가 딱 두 군데로 좁혀집니다. 이어붙인 줄에서 W의 마지막 팀과 T 사이, 그리고 T와 L의 첫 팀 사이예요. 첫 번째 이음매를 볼까요? W에 있는 팀은 정의상 모두 T를 이겼습니다. 그러니 W 순서의 맨 마지막 팀도 당연히 T를 이겼죠. 두 번째 이음매도 마찬가지예요. L에 있는 팀은 모두 T에게 졌으니 T는 L의 첫 팀을 이깁니다. 한쪽이 비어 있어도 괜찮습니다. W나 L의 크기가 0이면 그쪽은 그냥 사라지고 따질 경계도 없거든요. 이게 강한 귀납법이 돌아가는 방식 그대로예요. n짜리 문제를 더 작은 문제로 가르고 각 조각에 가정을 쓰고 합치는 방식이 성질을 지킨다라는 걸 보이는 거죠. 오늘 핵심 그림을 한 줄로 정리해 볼게요. 기준팀 하나를 고르고 나머지를 그 팀과의 승패로 가릅니다. 작아진 두 대진을 각각 풀고 그 답을 다시 이어 붙이는 거죠. 두 조각을 동시에 풀 수 있게 해준 게 바로 강한 귀납법입니다. 두 조각의 크기는 n보다 작기만 하면 0이어도 상관없거든요. 그리고 이어 붙인 뒤 위험한 곳은 기준팀 양옆 두 경계뿐이었습니다. 그 두 경계는 W와 L을 어떻게 나눴는지에서 곧바로 보장됐죠. 이렇게 가르고 합치는 방식은 앞으로 더 강한 형태로 다시 나옵니다. 그땐 나누는 게 어려운 게 아니라 다시 합칠 때 원하는 성질이 지켜지는지를 증명하는 게 관건이 될 거예요.